Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 53, and it is entitled Torque. So far, when we've talked about the motion of objects, we have treated objects as if they were point particles. And we've talked about the movement of objects, specifically the center of mass of objects, through space. We call this movement through space translation. An object has translated from one point to another. We haven't talked about the spinning of an object. What happens when an object actually begins to rotate? It turns out that it's possible to break the motion, any kind of motion of an object, down into translation and into rotation. And what we want to do now is to begin to take up rotational dynamics. So we need to begin to talk about what causes rotations to change, and that is torque. I've put changes in parentheses in this definition, torque being the cause of changes in rotational motion, because we're going to see torque plays the same role in rotations that forces do for translation. It turns out that in order to cause an object to change its translation, there has to be an unbalanced force. And likewise, to cause a change in the object's rotation, there has to be an unbalanced torque. Let's go to the playground. And I want you to think about a teeter-totter, a seesaw. There are certain parts of this apparatus that have technical names that you need to know. One of those is called the fulcrum. And the fulcrum is the pivot point around which the rotation takes place. Now you could imagine somebody sitting on one end of this teeter-totter. If there's just one person and they sit on one end, then the teeter-totter is going to be unbalanced, and it's going to tend to rotate either in a clockwise direction or a counterclockwise direction, depending on which side the person sits on. So now, if I sit on the left side of this teeter-totter, you can see that there's going to be a rotation that occurs, in this case, in the counterclockwise direction. And we would say that this person exerts a counterclockwise torque on the teeter-totter. How much torque is exerted? Well, we have to know something about how much force that the person exerts, which in this case is going to be equivalent to their weight, and how far from the fulcrum that weight is exerted. And that distance between the fulcrum and the application of the force, that's called the lever arm. The way this diagram is sketched, the force is applied perpendicular to the lever arm, and for 95% of the problems that you're going to solve, that's going to be the way that the force is applied. There will sometimes be a force applied at some angle, and you have to be able to handle those situations as well. But let's write down now the definition of torque and see how it applies in this particular situation. The torque, tau, is equal to R cross F. R being the lever arm and F being the force that's applied on that lever arm. This is a vector product. This is another cross product, just as we've seen when we dealt with the magnetic force on moving charges in a magnetic field. Numerically, the way that we write this is in terms of magnitudes. So I can say that the torque is equal to R times F times the sine of the angle between R and F. Let's talk about units for a moment. R has units of meters. F has units of newtons. The sine of an angle is just going to be a number. So the units of torque are going to be meters times newtons. Now we've dealt with newtons times meters before. We call that a joule. Meters times newtons, a unit of torque, that has the same dimensions, but they are not the same thing. Meters times newtons in this situation is not telling you the amount of energy or the amount of work that's being done. It's just telling you what the torque is that's applied to the object. We have to deal with signs, sign conventions, and I choose to use a sign convention that's a little bit different than your textbook. Your textbook calls clockwise torques positive and counterclockwise torques negative. I do the opposite sign convention. The reason for that is that that's what 90% of all other physics teachers and physics texts use. So be aware of the sign convention differences. It's not a big deal as long as you call one direction positive and the other direction negative. and deal with the signs appropriately. Now let's take a look at this R cross F business a little bit more. And so what's been reproduced here is a diagram that's in your textbook that shows the lever arm and a force that's applied at some angle that's theta. I could choose to resolve this force into components that are parallel and perpendicular to the lever arm. So let's look first at resolving the force into components. So you could look at this force triangle. The hypotenuse is F. The part that is parallel to the lever arm is the X component, which would be F times the cosine of the angle between R and F. And the Y component would be F times the sine of the angle. So now, if you want to think about these two forces being applied at the edge of the lever arm, then what I've got is an F cos theta that is parallel to the lever arm and an F times the sine of theta that is perpendicular to the lever arm. Which one of these is going to cause rotation? Well, it's the F sine theta that's going to cause the rotation. So if my pivot point, my fulcrum, is over here on the left-hand side, then what I would say is that the torque is equal to R times the force, the component of the force that's causing the rotation, F times the sine of theta. That's one way of looking at the torque. Here's another way, and this way involves, instead of resolving the force into components, resolving the lever arm or the moment arm into components. So you could think of this triangle, the lever arm forming a triangle that has a side that's parallel to the force and a side that's perpendicular to the force. So if R is the hypotenuse of that triangle, then the part that is parallel to the force is R times the cosine of theta, and the part that's perpendicular to the force is R times the sine of theta. The part that's going to be rotating, the part that is effectively being pushed by this force over here, is going to be the R sine theta component. So you could think of the torque is equal to R times sine theta, that's the effective moment arm or lever arm, times the force. So another way you could think about it is R sine theta times F. You can see whether I think of it in terms of the force being resolved into components or the moment arm being resolved into components. Essentially, I get the same numerical value for the torque when I put those things together. Now, why do we care about torques? Well, one reason we care about them is because they're on the AP exam. But really, the reason we care about them in physics is that oftentimes we want to figure out equilibrium situations. When is an object going to be not just in translational equilibrium, but in rotational equilibrium? And so we want to write down the conditions of equilibrium for an object. Basically, what we want to say is that the net force acting on the object is equal to 0. That's one condition of equilibrium. This is for translation. But for rotation, we also want to say that the net torques around some pivot point are equal to 0. And this is a condition of rotational equilibrium. When both of those conditions are met, then we say the object is in dynamic equilibrium. If I've got a sign that's hanging outside someone's office and there's a guy wire that supports the sign, there are going to be all sorts of questions that could be asked. How much tension is there in the guy wire? How much weight can the support have? How hard is the building pushing on the object, and in which direction will the net force that the building exerts on the lever be? All of those are sorts of questions that are going to come up. So let's take a look at some numerical examples to figure out how to approach these. The first example, a lady pushes with a force of 25 newtons on the end of a door that's 92 centimeters wide. A. Determine the torque she produces if the force is exerted perpendicular to the door. And B. Determine the torque she produces if the force is exerted at an angle of 50 degrees to the face of the door. We want to actually calculate what these torques are. Let's take a bird's eye view of the door for part A. So I have a door. I'm looking down maybe on the top of the door. And maybe the doorknob of the door is over here on the right-hand side. the hinge of the door is going to be over on the left-hand side. And we're going to call the hinge the pivot point. So this is going to be the fulcrum. It's going to pivot about that point. They say that the lady pushes with a force of 25 newtons on the end of a door that's 92 centimeters wide. Let's figure out the torque if the force is perpendicular to the door. So let's take this applied force that she is exerting and make it perpendicular to the door. So my force here is 25 newtons, and the distance that that force is applied from the pivot point is 92 centimeters, or 0.92 meters. That's going to be the lever arm. From the pivot point to the point where the force is applied is what we're going to call R. Now the angle between the force and the pivot lever arm, the moment arm, is 90 degrees. So I can say that the torque is going to be equal to R cross F, and that's going to be equal to R times F times the sine of the angle between them. But since the angle is 90 degrees, in this case, the sine of 90 degrees is equal to 1, so essentially in magnitudes the torque is going to be R times F, which in this case is 0.92 meters times the 25 newtons, and then I put that into my calculator and figure out what the number is. The number is 22.5 meter newtons. Now, let's not push perpendicular to the doorknob. Let's push at an angle of 50 degrees to the face of the door. And it doesn't matter whether the 50 degrees is to the left or the 50 degrees is to the right. I'm going to draw it one of those ways. So now maybe she's pulling on the doorknob at some angle that's 50 degrees with respect to the face of the door. Well, the moment arm is still going to be here, this 92 centimeters. The angle, though, is 50 degrees. So I'm going to have to work that into my torque equation. Is going to be R cross F, which is R times F times the sine of the angle between them. So this is my 0.92 meters times the 25 newtons times the sine now of 50 degrees. And I've got to figure out in magnitude, and I get 17.6 meters times newtons. That's a fairly straightforward application of figuring out torques.